Welcome to PDMA Corporation, home of the MC Emacs. I'd like to thank you for joining us as we continue along in our presentation series. Once again, my name is Todd Gunderson, the Vice President of Sales and Marketing, and as always, we are welcomed by our Vice President of Product Development, Mr. Noah Bethel.
Hello from sunny Tampa, Florida.
And as always, we truly appreciate our customer base as they constantly provide us with a tremendous amount of data, and in this case, pressure. What does that mean?
Different things to different people,
Different
right?
things, different people. But when it comes to motors and applications, that's always bad.
Oh yes,
right?
Pressure's never a good thing.
Never good. And so in this case here, we're going to talk about what happens to the process when an ID fan goes down. Okay, so an induced fan goes down. So here's our nameplate information. We have a Westinghouse 50 hertz, 3.3 kV voltage, 204 full load amps. So we're talking about a pretty large motor here.
Very decent sized motor, and coming to us from internationally, which is always interesting.
Right. So and you bring up a great point. This is from Indonesia, a cement factory in Indonesia that provided us this data. So it's 1,250 horsepower or 932 kilowatts. 6-pole motor, 994 RPM. So it's a fairly slow rolling motor.
Relative. It is, yes. And then based on the case study that you had mentioned, it's interesting that a lower RPM motor is suspicious of having broken rotor bars.
And we said it's an ID fan. It's an induced fan, so it's designed to provide air outlet of the system. So if pressure builds up too much, you could possibly have an explosion.
Yeah, I saw that reference to explosion on the notes, and I'm thinking, well, explosion's another word that not generally a good word around an industrial environment.
No, those never end up well. So here's a picture of the motor, and we can see it's a fairly large size, physically large, and we're also on the left-hand side of this. We're seeing where they're hooking up with the MC Emacs, our Emacs test leads, and they're getting current samples. Now, we could also have MTAPs installed here, so you don't have to do this type of testing where you hook up to the Tesla or where you hook up to the live lead connections.
Absolutely, yeah. This is not the most friendly cabinet to get into, like any of them. And a lot of bolts are designed to hold that on. It is clean. It's a clean environment as far as the maintenance that they're performing on the switchgear looks good. Cables look really well managed. And but still, if you don't have to take that door off, it'd be a good thing.
Right. So when this motor goes down, or if it goes down during production, everything stops because you need this fan in place, or else the furnace shuts down.
Right.
So it's very important. So we went out, we did a one-time test because we heard some noise and there was some heat, so it prompted the technician to go out and do a test, and lo and behold, what do we see? Pole pass sideband on our first test.
Yeah, and that's and you look, it's above the caution line. This is a relatively elevated pole pass frequency, and you hate to see that on the first test.
Especially with a motor that was recently installed, probably they said February of 2014. So relatively less than a year maybe in service.
Yeah, that's short term, and ideally this would be more of a second or third test in that situation.
Ideally it would be. So let's do some further evaluation. We go out to our fifth harmonic. Now, what does this tell us?
The fifth harmonic is a second test to help us solidify whether the pole pass frequency seen in the previous graph is coming from more likely a mechanical or a load-based anomaly, or whether it actually is coming from a magnetically induced anomaly from the rotor. It's been a great test for us. It's one of the how many methods that we offer for rotor evaluation. For those of you that get tip of the week, we talk about this swirl effect, as we call it, and certainly it is indicative of a phase shift in the rotor flux on or around a broken or cracked bar.
Now in this case here, you see, since it's 50 hertz system, it's at 250. That's the fifth harmonic. If it were a 60 hertz system, it would be pushed out a little further at the 300 hertz. We would expect to see those three peaks if we had issues with our rotor bars.
Correct.
So next, we do our DMOD. And in the DMOD test, we can see a pretty highly elevated pole pass sideband as well.
Right. We strip out all the, the basic fundamental frequency information, which allows us to look more isolated at the pole pass frequency, and it surely sticks out. We have this sort of minimum acceptable value of about zero.3, and if it gets up above that, we start to raise the flag of concern. In this situation, a caution pole pass in the initial graph is indicative of a problem, and now we can confirm it with the third indicator, which is the demodded spectrum above 0.3.
And now what's also interesting, in the notes, the technician noted that he was hearing sound at about 0.58 hertz, which when we look at our FFT and our demodulation spectrum, that's where this peak exists at, right around 0.58.
And that's good correlation, right? And not always do you get that kind of good correlation. Vibration readings will a lot of times be intermittent for a rotor anomaly. And when you see it, you want to try to get the current spectrum involved and see if you can correlate those two. In this situation, it was a great correlation, both at the same frequency. Vibration elevated at 0.58 hertz, current spectrums elevated at 0.58 hertz. It's kind of a great marriage of information.
And then lastly, we can look at our go-to test, which really is a nice look at our inrush startup. You don't just need it for inrush, you can use it for process analysis, and you can see some pretty substantial current swings here.
Yeah, we really like the envelope current for, like you said, Todd, process analysis, load, analysis. And in this situation, when you're talking about a fan, right, you wouldn't expect a lot of variation unless the load is driving it. So you do got to know the load a little bit. But in this situation, we're looking at about what appears to be 10% of full load amperage swings, and that's just not something you'd expect from an ID fan.
So let's look at we pull it apart, and wow, we see something pretty substantial. Almost to the point where you wonder if, since it's just the one crack here, pretty significant crack.
Yeah, I'm thinking like you. This is, motor's been installed less than a year probably. This is unfortunately the first test we took. It's hard for me to look at that crack and think that it hasn't been around for a while. And then, of course, you see the burning lamination tips at the open slot, and all that leads to a big concern that this has been running like this for a while.
And it runs along the whole bar, and we're essentially, current is flowing where on this now, Noah, because the bar is broken?
Right. By design, the current without the bar broken would flow right down that bar. But instead, when you don't have the bar to conduct from the in-ring, the flux that is creating the torque around this motor, it's going to complete a path one way or the other. So it starts to try to send current actually down the tips of the laminations, and they're just not designed to handle that. So it starts to burn the tips of those insulation and the laminations up, and as a result opens the slot a little bit more for the unfortunate possible future of the bar coming out of the slot.
Yeah. Now, what's interesting, and we always talk about this, when you have a rotor problem, yes, of course it has to be fixed, but there are some things that you can do to prolong that fix and satisfy the needs of production.
Right, and if you're looking at shutting down for a big loss versus running a motor with a defect, obviously you got to make a hard decision. But you're absolutely right. There's a lot of things you can do to minimize the stress on that rotor, to prolong the life, and to continue to produce product. The first one, minimize stopping and starting. The most stressful time of a motor's running operation is when you start it. Okay, variable frequency drives help that a little bit. In this situation, we're not dealing with that. It's across the line, so a lot of currents flowing through the bars and unfortunately across those laminations during starting and stopping. So that's a big issue. Minimizing load fluctuations. This is a lot of times up to an operational requirement. If the operations can steady state this, knowing that there's a rotor defect, it's going to reduce the amount of fluctuating currents, which are going to increase and decrease of slip on the motor, which is of course going to cause more current to flow down the broken bar. Increasing the monitoring frequency. Obviously, if you know there's a problem, let's make sure it's not going vertical. And so you increase the monitoring frequency to trend this more often to make sure that you can stop something before it goes catastrophic. Know your rotor design, open versus closed. In this picture you saw was an open bar design. So as the laminations start to burn off the tips and that opening gets larger, the fear of that bar coming out of that slot and slamming into the stator windings possibly doubles or triples the repair costs. So knowing if it's a closed or open bar design, because if this rotor was closed bar, Even if you have a broken bar, it's not coming out of the slot, right? And then finally, rotor speed. This is a relatively slow motor, so the centrifugal forces that might actually push that bar out are much less, which lowers the risk. So being able to take these things into account help you to at least understand the severity and maybe take some actions to prolong the life of the defective rotor.
And to put some numbers to this specific asset, the cost, had it failed prematurely or during a production run, would have been in excess of 750,000 US dollars to 1.1 million US dollars. And that's significant regardless of what plant you're at. That's a lot of money.
Oh yeah, that kind of money gets heads turning. It certainly warrants some hard decisions to be made, and I think in this situation they were able to to save production at the risk of making the problem a little worse.
Right. Well, we would like to thank you for your time. As always, we appreciate you watching or viewing our video presentations. If you have a video case study or a case study that you would like to present to us, please feel free to give us a call or view our website at www.pdma.com or call us at 813-621-6463. There, if you come to our website, you'll see a tremendous amount of information from additional case studies to our Tips of the Week archives. So I encourage you to, when you get a chance, to come take a look at us. Once again, thank you, Noah.
Thank you, Todd.
And we look forward to seeing you real soon.